repetition in this chapter as well. So Chemistry 3101, this is chapter 9, alkynes. And as I was just telling my students before I started recording here, a lot of the concepts that you see in chapter 8 are found in this chapter. So it's kind of a continuation of chapter 8. So you kind of go from chapter 8 and then you kind of continue on into 9. So things like hydroboration, oxidation are going to come up in this chapter. Markovnikov addition, anti-Markovnikov addition, elimination, hydration, that kind of stuff is going to come up over and over in this chapter. And so those are all words that you're familiar with. So also another thing that we were just discussing is what is the simplest possible alkyne in the universe? Well, the simplest alkyne you could have would be an alkyne with 2 carbons. It would be this, okay? So a 2-carbon alkyne. And you could draw it this way, or you can do a condensed form like this. Remember, you always have to show a double or a triple bond. Or if you do a bond line structure, it would just be this. And the name of this alkyne is acetylene. Acetylene. Okay, now that's the common name. If you're wondering, well, doesn't it have a systematic name? Yes, it would be ethyne. It would be ethyne, but very, very few people would use this. In fact, I don't think anybody really uses this. But again, it is acceptable. All right, so let's get into it here. And we'll start by looking at an orbital overlap diagram of acetylene. Okay, so this is actually an orbital overlap diagram of acetylene, as I just said, okay, which is the simplest possible alkyne. So this is what we're seeing, is this molecule here. They're just showing you all the orbitals that make up this molecule. So if I just move this structure over here, you guys are all perfectly aware that the first bond between any 2 atoms is always a sigma bond. So we could label these as sigma bonds. And how do you form sigma bonds? Well, they come from the head-to-head overlap of orbitals. And you see a hydrogen atom here, which has a 1s orbital. That's overlapping with the sp orbital from this carbon. And of course, that carbon has 2 sp orbitals. And so the other one is over here. We have another one here, and those 2 overlap to make a sigma bond. So we have a sigma bond here. This is obviously a sigma bond. I highlighted it for us here. And then we have another sp orbital, and of course this hydrogen is a 1s. And so this is a sigma bond. So we see the 3 sigma bonds. It's the head-to-head overlap here of the sp orbital from the carbon and the 1s orbital from the hydrogen. It's also the head-to-head overlap of the 2 sp orbitals from the 2 carbons that are both sp hybridized. And then the head-to-head overlap here of the sp hybrid orbital from the carbon on the right and the 1s orbital from the other hydrogen. Well, how do you form pi bonds? No mystery there. These are both pi bonds. Remember, a pi bond comes from the side-to-side overlap of p orbitals. And so what they're showing here is 2 p orbitals. I'll trace them out for you. So this would be 1 p orbital here on one carbon atom. This would be a p orbital on the neighboring carbon atom. And we don't actually draw them overlapping as I have it shown here. We just put these dashed lines in between, which kind of tells us they are touching. They are overlapping, okay? The other p orbital, I'm sure you can see it, is this one here, is perpendicular to the other p orbital, the one that I traced in black, and this one here. And you can see these are the lines that represent those orbitals touching, those p orbitals. So we have 2 pi bonds between the 2 of these. Now, another thing you're all perfectly aware of is the bond angle of an sp hybridized carbon is going to be 180 degrees. So its molecular geometry is linear. And so it's very difficult to put a triple bond in a ring. And if you go in the textbook, it even mentions cyclononine, and it says this molecule, decomposes very rapidly because it's, again, difficult to put a linear, two linear geometry carbons, adjacent to each other in a ring. Well, if you look at an electrostatic potential map of an alkyne, again, this is what we call an EPM, okay? The colors, the orange color represents delta negative and the blue color represents delta positive. So you see there's a lot of electron density in the center of the acetylene molecule. And again, this is just the simplest possible alkyne in the universe, okay, that we're using for instructional purposes here. The same thing would apply, to any alkyne here. It says, given the presence of pi bonds, alkynes, which we're going to cover in this chapter, chapter 9, are similar to alkenes that we studied in chapter 8. Well, that's good. And their ability to act as a nucleophile. And so many of the addition reactions of alkenes also work on alkynes. So things like hydration, we're going to see that come up. We're going to see hydrogenation. Hydrogenation is going to come up in this chapter, et cetera, et cetera. So again, remember that your bond angle is 180 degrees. The hybridization of the carbons is sp for each one of them. And since you have so much electron density in the center of that triple bond, an alkyne is capable of acting as a nucleophile or a base. Okay, you can do either one. So where do you find alkynes in industry and nature? Well, there's actually some really cool discussion about where you might find alkynes. It even gets into discussion of some contraceptives and Parkinson's medications. And this is in the textbook. I'm not going to go over it now, but you can read that on your own time. But as I stated, acetylene is the simplest possible alkyne. We usually write the structure like this, partially condensed, or even more frequently, we draw it like this. Okay, it's a bond line structure. Acetylene is used in blowtorches. Why? Because it makes a very hot flame. It makes a flame that's around, I don't know, around 2,800 degrees Celsius. So it's used for cutting metal. And I'm not an expert in welding, so please don't cut me down. No pun intended. You know, if I stated that incorrectly, exactly what it's used for. But again, not only are alkynes found in pharmaceuticals like Parkinson's medications or contraceptives. They're also found in natural products, and this is a really cool one here. If you know about Dendrobates histrionicus, which is the poison dart frog, this is the toxin that the frog emits. Anyhow, and I won't go into the whole, how the frog emits the poison. I won't get into how humans have collected that for millennia. But anyhow, you see that there's two triple bonds in here in this poisonous compound, and again, this is used it's isolated from the poison dart frog. And again, I'm not really an expert on that, but it's kind of a cool compound. All right, as far as nomenclature of alkynes goes, if you can name an alkane and an alkene, which you all can, you can name an alkyne, okay? You guys know all the alkyl groups: methyl, ethyl, propyl, isopropyl, butyl, terbutyl, secbutyl, isobutyl. I don't need to help you with that. And so all you have to do is kind of take the alkene nomenclature in a way and really just modify the suffix, okay, from ene to ine. So just like we saw with alkenes, the first thing we're going to do is we're going to find the longest parent chain. But what? It's got to contain the carbon-carbon triple bond. Just like with alkenes, it had to contain the double bond. We're going to identify and name all the substituents. Do we have a chloro, a fluoro, a methyl, an isopropyl, et cetera, et cetera? We give a locant. Remember, a locant is just a tsatsi name for a number. Okay, so don't get intimidated by locant. It's just a number and a prefix if necessary, right? 2,2-dimethyl, or if it's a 4-isopropyl or something like that. We have to give a locant, a number, and a prefix when we need to, di, tri, tetra, etc., for every substituent. And what's the rule that we follow is we give the carbon-carbon triple bond the lowest possible number, okay? So when we're numbering our carbon chain, right, let's say we have something like this, okay? The first one, so 1, 2, 3, 4, 5, or like that, the first number on the carbon of the triple bond is the number that we use to provide a locant for our triple bond. So this compound would be 2-pentyne, okay? So it'd be 2-pentyne, or you could call it pent-2-ine. Either one is acceptable. So you'll put the numbered substituents before the parent name, ignore the prefixes, iso, cyclo, that doesn't look very good, cyclo, and neo, when ordering alphabetically. And again, like I said, you can put the locant for the triple bond either just before the name, so like 2-pentyne, or you could put it right before the suffix. You could say pent-2-ine. Either one is totally acceptable, okay? They're both perfectly fine. So there are the 5 rules that we follow for naming alkynes. And again, if you knew how to name an alkene, you can name an alkyne. And so he just kind of walked through some examples here. Everybody knows pentane. Everybody knows pentene. It's not the complete name here, though, is it, right? You have to number it 1, 2, 3, 4, 5. We give the double bond the lowest possible number, so it's 1-pentene, or you could call it pent-1-ene. And then this compound here, this would be 1-pentyne, or you could call it pent-1-ene. Either one is totally fine. Now, if this compound here, you see that it's got this ethyl group on it, and the longest chain is the octane. Well, we still have the octane in here, but now it doesn't count as the parent. Why? Because it doesn't possess the triple bond. So this compound, you have to go with the chain that's highlighted in red. And so it's a 1-heptine. And if you count 1, 2, 3, you'd call this 3-propyl 1-heptine. Or you could call it 3-propyl heptonine. Either one is perfectly cool. Give me a thumbs up if you're with me on just the idea of the rules, okay? So far, is everybody with me on these rules? Okay, cool. Okay, now he goes into more detail here about things that you guys are all perfectly aware of. You know, incorrect and correct ways of numbering compounds. Well, I find that students generally don't struggle with this. Once they learn how to name an alkene and they know to give the double bond the lowest possible number, well, they know to do the same thing with a triple bond. So you can see here that this would be, if we did the Drake meme, you know, he'd be giving the thumbs up in his orange jacket. Right in here, he'd be turning away kind of thing. Anyhow, so the first one, it would be some kind of 2-heptine, and the second one, it's a 5-heptine, but that would be incorrect, right? Because you want to give the triple bond the lowest possible number. So here in this compound, we also have 1, 2, 3 methyl groups. So you would call this 5,5,6 trimethyl. So 5, 5, 6 trimethyl 2-heptine, like that. Anyhow, so there we go. Nothing really new with that. And I told you, you could put the locant for the triple bond either before the parent name or before the suffix. Either one is totally fine. Now, as far as common names go for alkynes, you guys have probably picked up on this by now, that organic chemists are really hung up on common names. They love them, okay? They just love them so much. And so if you know acetylene, which I told you, you could also call it ethine, but nobody ever calls it that. So it says here, common names derived of compounds derived from acetylene. We use those all the time. So you could call this compound here, you could call this propine. Okay, there's nothing wrong with that name. But you could also call it methylacetylene, right? It's like an acetylene, and then it's got a methyl group attached to it. Right, this one here is diisopropyl acetylene. 1, 2, 3, 4, 5, 6. Technically, you could call it 2,5. You could call it 2,5-dimethyl 3-hexyne. But again, nobody would do that, right? If it's an alkyl group that you recognize, like a phenyl or a butyl or something, or a terbutyl, right? You use those, right? Chemists or scientists love to use common names. So this one here, phenylpropyl, you just put them in alphabetical order from A to Z. So phenyl comes before propyl. So phenylpropyl acetylene. And then also, this is really important because I'm going to bring up terminal alkynes like Avogadro's number of times in this class, okay? So what a terminal alkyne is, it's when you have an alkyne that has a hydrogen attached to at least one of the carbons, okay, of the triple bond. Whereas, so this would be an example of a terminal alkyne, right? Oops. I guess I could just pencil in the hydrogen over here. There we go. So that would be an example of a terminal alkyne. And we're actually going to discuss terminal alkynes more than internal alkynes, believe it or not. But an internal alkyne is one where you have R, then your triple bond, then you have another R group. So neither of the carbons in the triple bond has a hydrogen attached directly to it. So again, internal and terminal alkynes. And again, we're going to spend way more time talking about terminal alkynes. If you want the reason why right away, I can tell you very quickly, okay? The reason why is because if you take a strong enough base, a strong base, you can deprotonate the triple bond or the hydrogen from the terminal alkyne, and then you end up with what's called an alkanide, and that's a good base, and it's also a good nucleophile. So now we're going to have a new way to make a new carbon-carbon bond. So that's why we spend so much time talking about terminal alkynes. Let's see if we can provide systematic. Let's do a double whammy here. Let's do systematic and common. We'll do both, okay, for each of the following compounds. So if I wanted to, let's just start with systematic. So I'll use blue for systematic and red for common. Okay, so let's say we wanted to give a systematic name for this compound. Could anybody tell me how many carbons are in the longest chain that contains the triple bond? Yeah, exactly. Thanks, Jenny. 6. Now, would I start numbering at the carbon in green or the carbon in red? Can anybody help me out with that? And it's not a trick. Yeah, absolutely. I should start numbering at the carbon in green, right? Because either way, I have 1, 2, 3, or 1, 2, 3. So either way, the triple bond has a locant of 3. But remember, if I go off the green carbon, then the methyl gets a lower number, right? So I want to give that methyl group, I go to the next rule, and I want to give the methyl the lowest possible number. So we have a 2 methyl, and then we have a 3 hexyne. So we'd call this 2 methyl 3 hexyne, or you could call it 2-methyl hex 3-ine. Those are both perfectly acceptable. But then as far as a common name goes, what we do for the common name is we look at just the triple bond, and then we just name the R groups that are attached to it. So on one side we have an isopropyl, and on the other side we have an ethyl. So E comes first, so we're going to say ethyl, isopropyl, acetylene, ethyl isopropyl acetylene. There we go. All right, for the next one, could anybody tell me how many carbons are in the longest chain that contains the triple bond? And again, it's not a trick question. How many carbons in the longest chain in this guy? Yeah, exactly. Thanks, Isaac. Yep, 4. So we're going to start numbering here. 1, 2, 3, 4. So we have a 3,3 dimethyl, 1 butyne. So 3, 3 dimethyl, 1, 1 butyne, like that. Yeah. Or you could call it 3,3 dimethyl but 1-ine. Either one is fine. And then as far as a common name goes, well, this one, there's just one alkyl group on it, so you just call it tert-butyl acetylene. Tert-butyl. There we go, tert-butyl acetylene. All right, both of them are perfectly acceptable. There you go. So again, like I said, my students are usually very good at naming alkynes because they spend so much time thinking about alkenes. And so to move into this chapter is not that much of a stretch. Well, let's get into the topic of acids and bases for a few minutes. Okay, I know you guys remember the concept of areo really well. So atom, resonance, induction, and orbital. And it's going to show up on the next slide because we're going to talk about the pKa of an alkane. So ethane is an alkane versus an alkene. Ethylene is an alkene. And then, of course, in this chapter, we're going to discuss alkynes. And this is something that we covered way back in chapter 4. So there's really nothing new on this slide. But you should remember that the pKa of an alkane is around 50. An alkene, when you have an sp2, hybridized carbon-hydrogen bond, that hydrogen is going to have a pK of around 44. And then for acetylene, you notice that, I mean, it's just way more acidic than an alkane or an alkene, right? Even if you compare it to an alkene, the sp hybridized carbon-hydrogen bond, that hydrogen has a pK of 25. So that's 10 to the 19 more acidic than ethylene. Is it a strong acid? Well, no, not even close. I mean, it's even less acidic than an alcohol. But the bottom line is there's a huge gap between here and here. So that means, or the conclusion is that alkynes are much more acidic than an alkene. Well, why is that? And we actually touched on this earlier on in the class, okay? It's because an sp hybrid orbital is a much smaller than an sp2 or an sp3 hybrid orbital. And so it's better able to stabilize the negative charge. And we're going to see that on this slide there. But before we get there, I just want to point out that because of the lower pKa of a terminal alkyne, and of course acetylene counts as a terminal alkyne because both of the carbons have a hydrogen attached to them in that triple bond. Well, it says here, acetylene can be deprotonated by a strong base. I don't know why it says strong based, but anyhow, it should just say a strong base to form the conjugate base, and we call that an acetylide ion. If you do the same thing with a terminal alkyne, and I'm going to show you this again, okay? But let's say you have a terminal alkyne. It doesn't matter what it is, but this is just some kind of generic alkyne, and you could put your terminal, okay? When you treat that with a base, okay, a really strong base, okay, I'll just put negative charge here. You're going to end up with this. And we don't call this an acetylide because it doesn't come from acetylene. It comes from an alkyne. So we call this an alkynide ion. Okay, so an alkynide ion. So just make sure you're aware of an acetylide and an alkynide. Okay, so again, what do we use to explain why acetylene is so much more acidic than ethylene? Well, we use ARIO. So if we go back to the acronym ARIO, we can't use atom. Why? Because the negative charge of the conjugate base of all of these is on a carbon. We can't use resonance because there's no resonance forms. We can't use induction. There's no electron withdrawing groups. And so we have to use orbital. So again, when you take ethane, CH3, and you deprotonate it, right, loss of H plus, you end up with this carbon ion, and the negative charge is in an sp3 hybrid orbital. If you do the same thing with ethylene, you deprotonate it, so you lose H plus, okay? Again, you use a strong base. The negative charge is in an sp2 hybrid orbital, and then when you do it with acetylene, well, when you lose H plus here, you end up with acetylide, okay? So this is the acetylide ion right here, okay? So what they're showing you here is this, okay? And why is that so stable, so much more stable than the other conjugate bases? It's because the negative charge is in a smaller orbital. An sp orbital is smaller, and if the orbital is smaller, that means the negative charge is closer to a nucleus, and what's the charge of a nucleus? It's positive. So there you go. Now that we've established that alkynes are much more acidic than alkenes or alkenes, let's see what kind of synthetic utility they have. But before we do that, we have to kind of figure out, okay, well, what would be an appropriate base, right? What would be a good base that I could use? You know, you might be wondering, well, DBU, DBN, you know, ethoxide, hydroxide, are these good bases? Well, that's what we're going to uncover right now. So let's take a look. And you guys know that when you compare, when you look at an acid-base reaction, so if this is our base, if this is our acid, this is our conjugate acid, this is our conjugate base, to what side does the equilibrium lie? The equilibrium lies to the side of the weaker acid. So this compound here, so NaNH2, this is called sodium amide, okay? Because the amide ion is this, NH2 minus, okay? If you draw a Lewis structure, you see that the Lewis structure is there, but this is the amide ion. And I know what an amide functional group is too. This is a different use of the word, so it's just the conjugate base of ammonia is all it is. So if you take sodium amide, which is a strong base, and you deprotonate acetylene to get the acetylide ion, in this case it's sodium acetylide, you end up with ammonia as the conjugate acid. Well, what's the pK of ammonia? Ammonia has a pK of around 38. So that means the equilibrium is going to lie to the side of the ammonia, which is the weaker acid. And so that means this is a good base for deprotonating a terminal alkyne, right? It will work. Now, you might be wondering, well, what about something like sodium hydroxide? I know that's a really strong base, and it is. Okay, it is a very strong base, but if you put sodium hydroxide in with your acetylene, you see the conjugate acid in this case is water, and water has a lower pK. It's a stronger acid than the terminal alkyne, and so hydroxide is not an appropriate base for deprotonating an alkyne. It doesn't work. Okay, you get some of the conjugate base, but it doesn't give you complete deprotonation. And so our take-home message is whether you want to make an acetylide or an alkynide. So we've gone over acetylide, which was, where's my black pen? We've gone over acetylide, which is this. You treat it with a base. Okay, you end up with acetylide. Okay, or if you have a terminal alkyne, you get an alkynide. The base that we most often use is sodium amide. Okay, so the base that we most often use is sodium amide because it works really well. So again, the name of this compound is sodium, which is our cation, amide. All right, there you go. And sodium amide, and you have to know how to draw the Lewis structure of the amide ion. Why? Because I expect you to be able to draw the mechanism of a deprotonation, which is a relatively straightforward mechanism. Now, it says it's often used as a base, but there are others as well. So let's take a look at some of the others. Okay, the one that we're going to use most of the time. Okay, and we're only really going to look at these three, or these ones right here. We're going to use sodium amide, or sorry, yeah, the amide ion most of the time. I'd say probably greater than 90% of the time. Why? Because it's the one he always uses in the textbook. But remember, this is called a hydride. So a hydride ion. That will also work. So you can get that from sodium hydride, or a butyl carbanion. So this comes from butyl lithium. So if you just write butyl lithium, right, because you need a cation here. So the butyl carbanion is basically what we're seeing here. That's a really strong base, okay? So we just call that the butyl carbanion. So the hydride, again, comes from sodium hydride. The butyl carbanion comes from butyl lithium. And then the amide ion comes from sodium amide. And you think about all these wonderful strong bases. I mean, if you go back to chapter 7, all of these bases were in the category of what? Strong base, strong nucleophile. But they are strong bases. There's no arguing that. But are they strong enough to deprotonate a terminal alkyne? No. Okay, they are strong bases. Again, you can't argue that. They're strong, but they're not strong enough. You've got to have a really strong base if you want to deprotonate an alkyne. So there you go. If you're wondering, like, why don't we use these really strong bases for everything? And, these guys are so strong. Well, they can be kind of dangerous to work with. Okay? They're not that easy to work with. And there's other reasons as well. But butyl lithium is pyrophoric. And if you're not sure what pyrophoric means, it means it ignites in air. So you have to be very careful. If you're saying, are you saying you can't even expose it to air and it catches on fire? You're right. Okay. So you can imagine that working with something that even if it's exposed to air causes a fire is hazardous. It's not easy, and so there's special techniques involved in that. So it can be, more cumbersome than pulling out some ethoxide, which you can totally leave open to the air. All right, so let's just get some practice here. There's nothing really mind-boggling in this one, but it just says in each of the following cases, determine if the base is sufficiently strong to deprotonate the terminal alkyne. Well, I know you guys can figure this out very quickly. So the first one, we have a terminal alkyne and we have sodium amide. So in that case, we would deprotonate to get the alkanide, okay? And then we would also end up with ammonia. Okay, so we get the sodium cation here. So that means this is our acid. This has a pKa that is equal to 25. And then we have our base, which is our sodium amide. We have our conjugate base, which is our alkanide. And then ammonia would be our conjugate acid, and it has a pKa that is equal to 36. And so the equilibrium is going to lie to the side of the weaker acid. And so we could say, yes, sodium amide is completely effective, and you know that because we saw it on the last slide. Same thing with the next one. So the next one, we have sodium hydride. And if you want to practice your mechanisms, you could draw the hydride ion and then say, well, it's going to do a deprotonation like this. I'm going to put the lone pair down here. So that is going to give me this alkanide. So I get this alkanide, and I have the sodium cation, which is a spectator. And then I have H2. Okay, now hydrogen gas does have a pKa, which was on the previous slide. So the pKa of our terminal alkyne is 25, and the pKa of H2 is around 35, I think is what they had on the previous slide. So yeah, they had 35. Oh, they had 38. Okay, so maybe I'll fix that one. So they had 35. I'll change this to an 8 here. It's close enough, but whatever. Come on, 38. There we go. So the equilibrium is going to lie to the side of the weaker acid. And so again, we'll write, yes, sodium hydride is totally effective at deprotonating a terminal alkyne. And let's take a look at the next one. So if we do a deprotonation, we could draw our tert butoxide ion, but I'm not going to do that right now. But if we were to deprotonate, we'd end up with this alkanide plus we'd end up with tert-butanol, okay, would be the conjugate acid. So this would be our acid, and it has a pKa that is equal to 25. And then our conjugate acid is tert-butanol, and you can see that tert-butanol has a pKa of 18. So we'll scribble that down here, pKa of 18. And you see that it is more acidic than a terminal alkyne, and so the equilibrium is actually going to lie to the left, and so no, this is not an appropriate base. So again, what are the appropriate bases? They are the hydride ion, okay, and we get that from, let me see here, we get that from sodium hydride, NaH. Then we have the amide ion. So the amide ion is NH2 minus, and we get that from sodium amide. And the last one is the butyl carbanion ion, okay, which is this here, and we get that from butyl lithium. So we just write BuLi because Li is the spectator ion, or is the cation. There you go. So those are the bases, and those are the sources of them that we're going to use to deprotonate alkynes. So if you're wondering, how do I make an alkyne? Well, you could, just go into the kitchen and get some flour. I'm kidding. Anyhow, how do you make an alkyne? There's a couple of ways that we can make alkynes, but let's start off by talking about elimination. You guys remember this reaction, this chestnut from section 8.7 of chapter 8. If you take a strong base, I'll just write base, some generic base here, okay? What that's going to do here is that can do a proton transfer, form a double bond, right, like this. So I just drew the mechanism of an E2 reaction is all I did to form a double bond. So you can imagine that if you have two halogens on the same carbon and then two hydrogens on the adjacent carbon, you can do two E2 reactions. So you basically do 2 times an E2, right? The first one is going to give you this, or is going to give you an alkene, something like this, okay? And then you do it again, okay, the same old mechanism again. So you do 2 eliminations in a row. So you see the mechanism is shown here, okay? So I expect you to know this mechanism, okay, which is just a double E2 reaction, right? This is an E2 and this is an E2. There's nothing new here at all. Now notice that when you have 2 bromines or 2 leaving groups on the same carbon, we call that geminal, okay, which is like Gemini, twins, right? They're on the same atom. Whereas if they're on neighboring carbons, we call that vicinal. So we see that these 2 bromines here are vicinal, but you could do the exact same thing here, right? You could do E2, and then another E2, and then you're going to end up with an alkyne, okay? So either way, get it? Either way works. All right, there you go. So that's how you make an alkyne, is you take a vicinal or a geminal dihalide. You got to have hydrogens in the right place. Then you do a double elimination, and then you form your alkyne. And we're going to see this more as we move on. So the story isn't complete yet, is what I would say about this. Now, why is that? Because, check this out. Let's say you took your geminal dihalide here. So if you're not paying attention, just wake up for a sec, okay? Let's say you took this geminal dihalide and you treated it with excess sodium amide in ammonia, okay? What are you going to get? Well, after the double elimination, you're actually going to get this compound. You're going to get the terminal alkyne. But hold the phone. If you have a bunch of amide in here, what it's going to do is it's basic enough to rip this proton off. And so you actually end up with the alkynide ion in the end. So again, let me repeat this, is if you were to take this compound, so we'll just write RCH2, CHBr2, okay? So that's just the condensed form of this compound, okay? So if you took that compound and you treated it with excess sodium amide, what you're actually going to end up with is this, you're going to end up with an alkynide ion. And so you need a second step, which is you need to throw in some water, okay, to protonate, and then you're going to end up with the terminal alkyne like that. So if you want to do your double elimination to produce a terminal alkyne, what you have to do is a 2-step process. Step 1 is going to be excess sodium amide, and step 2 is going to be water to protonate the terminal alkyne that's formed. So it says here, overall, a terminal alkyne is prepared by treating the dihalide with excess sodium amide followed by water. So what we're going to do is, do I have enough room to draw the whole dang mechanism here? Well, actually, the next question, or the first question, actually wants us to draw some mechanism. So let's get some practice on this. I only have room to do this one on this slide, but we'll go somewhere else to do the other one. Okay, so we're taking this dibromo compound here. Would you describe these bromines as geminal or vicinal? Can anybody answer that? And it's not a trick. Would you classify those as geminal or vicinal, those two bromines? Anybody? Geminal or vicinal for those two bromines? They're geminal, right? Thanks, Hannah. Yeah, because they're on the same carbon. Yeah, so geminal. So what we're going to do is there are 3 protons on this carbon here. There are no protons on this one, so those are the only beta protons we have. So I'm going to eliminate those, but I'll put one in for instructional purposes. So we'll put our amide ion, and let's do our first E2. So I'll use a different color here. So we're going to pull off this proton, form a double bond, lose our bromine, and then what do we end up with? We end up with something that looks like this. Now, oops, I have my double bond in the right place, don't I? Anyhow, so now I have this bromine, all right? Yeah. What am I doing here? So 1, 2, 3. There we go. I was like, something wrong with my structure. There we go. I had the bromine in the wrong place. There we go. That's a little better. Okay. So now what we're going to do is we're going to do the next elimination. I know there's 2 protons here. I'm fully aware of that. I'm just going to put 1 in for instructional purposes. I certainly don't want to confuse myself again. So we'll draw another amide ion. So NH2 minus. Remember, there's excess. So there's more than enough to do the job. So we're going to do another elimination like this. So there we go. So now we end up with this. So now we end up with our terminal alkyne, and we have a proton there. So you might think we're done. You might be like, well, there you go. Mechanism complete. No, because we have excess sodium amide. So another equivalent of sodium amide, a third one, is going to come in, and it's going to deprotonate here to give us the alkanide. Right? So we end up with the terminal alkanide like this, and then we put in the water. So we put in some water like this, okay? And so that's going to do a proton transfer like this, and that gives us the terminal alkyne. There we go. So we end up with this compound like that. Now that's a mechanism I expect you to be able to draw, okay? Is the double elimination with a geminal dihalide. So again, I'll scribble that in here. These two are geminal, okay, and these two here are vicinal. So you've got to know how to do both. So let's go over to a blank document, and we'll give this one the old college try. Just bear with me here. There we go. So I got it all ready to go. So for this one, again, we're going to make the same alkyne. So I figured that we're going to do that. But let's just get some practice on drawing the mechanism. So we're going to do our first elimination. So I'll put in a red proton here, and we're going to abstract that proton. That's not a very good arrow, like that. Okay, lose our leaving group, and that is going to give us something that looks like this. So now we've got our double bond, we've got our chlorine here, and now we've got a proton here. So the next equivalent of the amide ion, NH2 minus, is going to come in, and it's going to grab this proton, and we're going to lose this leaving group. Then we end up with what is going to be the final product. But are we done? We'll put here done. And the answer is no. Why? Because we have excess sodium amide. And so, I'll draw it like this. We have excess sodium amide. So a third amide ion, which is our base, is going to come along and pull off this proton. And we are going to have the alkanide ion like that. And then to get to the end here, We're going to have a water molecule act as an acid, and the alkanide is going to pick up the proton from that. And there you have it. And again, this is a mechanism that I expect you to be able to draw. So with a geminal dihalide or a vicinal dihalide, you should be able to do this double elimination followed by deprotonation, followed by protonation in the end. Okay, so it's a two-step process to make a terminal alkyne like that. All right, so let's go back to our slides and we'll see that we've already covered we've covered section 1, which is kind of an introduction to alkynes. Then we covered section 2, which is just nomenclature. And we went through that. We even got a little practice on that. And then we did a little section on pKa and how do you know what's an appropriate base to deprotonate a terminal alkyne. We talked about the difference between an alkanide ion, okay, and an acetylide ion. Since we usually use sodium amide or sodium hydride, the cation to these is more often than not is going to be sodium. So we use sodium acetylide a lot as a reagent. So we went over the explanation of the pKa. All right, so we covered all that. And then we looked at how to prepare an alkyne, okay, which is just a double elimination followed by deprotonation and then a proton transfer after you put in some water at the end. And we even get some practice on the mechanism of this reaction, and that's a mechanism that I expect you to be able to draw. So the next section is going to deal with hydrogenation of an alkyne.